This lecture is about electric potential, or also known as voltage. Now before we begin, recall a couple of things. First, recall the electric field and how we defined it. The electric field was defined such that multiplying it by the charge gives the electric force. Defined that way, the electric field was just the electric force divided by some test charge. It's good to recall this because voltage is defined in an analogous way. A voltage times a charge gives the potential energy electric, just like an electric field times a charge gave a force electric. Similarly, this definition of voltage means that the voltage is the potential energy electric divided by Q, analogous to the relationship with the electric field and the force. Second, recall that for any force, the work done by that force is the product of that force with the displacement. Now this is for a constant force. If the force is varying, you have to do an integral. And the work done by a force is equal to minus the change in potential energy associated with that force. This is only for conservative forces, but the electric force is a conservative force. Recall also the examples we did of work and potential energy. Specifically, we did the force due to gravity near the Earth's surface is just a constant, minus mg, and this implied that the potential energy due to gravity was mgh. Recall another particular case we did of the force due to gravity for any two objects, mass big M and little m, and a distance r squared apart, for example, planets. And in that case, we talked about how the potential energy due to gravity is equal to minus gmm over r. So the gmm over r squared force gave a potential energy of minus gmm over r. Now, with electric potential energy, considering the case of a uniform electric field analogous to the uniform gravitational field on or near the Earth's surface, what we find is that the work done due to the electric force is equal to the force electric times delta x, of course, that's definition of work, and that's got to be equal to minus the change in the potential energy, definition of potential energy. And so putting in for the force electric Q times E, and putting in for the change in potential energy, Q times delta V, we get this relationship here. The charges cancel out, leaving us with the relationship delta V equals minus E times delta X. Now remember, this relationship is really only usable for a uniform electric field, otherwise you have to do an integral. Now, recalling that the Coulomb force due to an electric point charge, takes the same form as the gravitational force, it's the same thing just with different letters. Instead of gmm over r squared, we have kqqq over r squared. We can write in an analogous way to the way we wrote the gravitational potential energy, we can write the electric potential energy. So that's kqqq over r, just like potential energy gravitational is gmm over r, we just have different letters. Note that the minus sign is not present. That's because in gravitation, like charges attract, but in electrostatic force, like charges repel. So it's different by a minus sign. We can now divide both sides by Q to get by little q, to get that the voltage due to a point charge is kq over r. Remember, that's specifically for the voltage due to a point charge. The basic important things here then are the definition of voltage, which you can rearrange, the voltage due to a uniform electric field, and the voltage due to a point charge. So what can we do with this? Well, this now allows us to apply conservation of energy to electric forces. So let's take a moment and consider a parallel plate capacitor. We talked about this charge configuration before. A bunch of positive charges uniformly distributed in a line and a bunch of negative charges uniformly distributed in a line. And this results in an electric field that's approximately uniform. Now, when dealing with real electronics, we often talk about voltages. So, let's say that this voltage difference is 1 volt. And by the way, I forgot to talk about units. Voltage is a potential energy divided by an electric charge. So in terms of units, that means that it is some number of joules per coulomb. And a joule per coulomb is conventionally just called a volt. Now, be careful about this because you could wind up writing statements like voltage equals 3 volts. And it's important to remember that this is referring to the electric potential, and this V is referring to the unit in which you're writing the electric potential, so you can't just go and cancel out these two V's and then get 1 equals 3. Okay? V gets used in multiple different ways, so be careful about that. Coming back to our problem, we could ask in this parallel plate capacitor, how much velocity would be gained by an electron that starts on the negative side with 0 initial velocity and falls essentially to the positive side. Now remember, the electron's moving opposite the direction of the electric field because it has a negative charge. We can use the fact that the change in potential energy electric is equal to the change in kinetic energy. No other forces going on in this problem. And then we can write the electric potential energy in terms of the charge and the change in voltage from the previous slide. And kinetic energy is just what it usually is. We get that the velocity is square root 2qv over m. Now the charge for an electron is 1.6 times 10 to the minus 19. The mass of an electron is 9.1 times 10 to the minus 31 kilograms. And putting in those numbers, I found that the velocity was 5.9 times 10 to the 5th meters per second. Now we can do another problem with this setup. We can say, what if the distance between this positively charged plate and this negatively charged parallel plate is 1 millimeter? What then is the electric field in between them? Well, using the definition of voltage in terms of electric field, the electric field is just delta V over delta X. And I guess there's supposed to be a minus sign in there. Putting in numbers, we get 1,000 newtons per coulomb. Now, note that the volt is the standard international unit for electric potential. So as long as we're staying in standard international units, when we get an electric field, the result will be in the standard international units for electric field. I am being imprecise about the minus sign here. What's going on is that this side is really at the higher electric potential, and this is at the lower electric potential. So as we go from this side to this side, the change in voltage would actually be negative. So the plus 1V would be if we're going from this side to this side, minus 1V would be the change in voltage if we go from this side to this side. The important thing about the sign here is that we know what direction we're talking about. So it's 1,000 newtons per coulomb from the positive side to the negative side of the plate, because remember, it's the direction that a positive charge would go, and a positive charge, positive test charge, would want to get away from the plus charges and go toward the negative charges. So that's the direction of this 1,000 newtons per coulomb electric field. And in that direction, you're actually going from a higher voltage to a lower voltage, a higher electric potential to a lower electric potential, because that's what things do. They always want to go to a lower potential energy. They want to go down the hill. Let's do a homework problem. Once again, we have a parallel plate capacitor, and let's say the voltage difference between the two sides is 0.5 volts. The distance between the two sides is 2 millimeters. Part A, what is the electric field between the plates? Part B, what is the acceleration of an electron in between the two plates? This is just due to the electric field between the plates, no other forces. C, How fast would an electron be going after traveling from one plate to the other starting from rest? Of course, it'll be traveling from the negative plate to the positive plate starting from rest. Solve this one using kinematics. That is, use the acceleration that you got in part B and the distance the electron has to travel to find out how fast it would be going. Part D, now answer the same question as C, but this time use energy and voltage instead of kinematics and acceleration. You should get the same answer. Let's do another example problem. This time we'll deal with some point charges. Let's suppose we have 2 point charges, one positive and one negative, in free space, so no other forces exerted on them. One has a charge of 10 to the minus 7 coulombs. The negative one will have a charge of minus 10 to the minus 6 coulombs. And let's let them start 1 meter apart. Let's give them each a mass of 1 gram, and let's ask the question, how fast would they be going? How fast would they be going? What would be V final once they have fallen toward each other and now have a separation of, let's say 0.1 meters. So we'll call that D2 is 0.1 meters. Or actually, let's call it D final. We'll call the initial distance D initial 1 meter. They start at a distance apart D initial, and they start at rest with 0 velocity. And so the question is then, what is the final velocity? Well, the initial energy is just the electric potential energy, which is K Q1 Q2 over D. And by the way, that's coming from the fact that the potential energy electric is equal to the voltage times, we'll say, the charge Q2. And the voltage due to a point charge is K Q1 over D initial, which is the radius, the distance between the two. And so we're taking the voltage due to the charge Q1 and multiplying it by the charge Q2 to get the electric potential energy. And that's the initial energy in this problem. Note that we did this by getting the voltage due to charge Q1 and multiplying it by Q2 to get the potential energy. We could equally well have gotten the voltage due to Q2 and multiplied by Q1. We would have gotten the same result. The final energy is just going to be the final electric potential energy plus 2 times the kinetic energy of one of these particles. Now, the reason that there's a 2 here is, first of all, we have to account for the kinetic energy of both of them. And note that the force that they exert on each other is going to be equal. The force exerted on Q1 by Q2 is equal to the force exerted on Q2 by Q1, equal except opposite. That's because of Newton's law. And also their masses are the same. So if their masses are the same and the forces exerted on them are the same, then their velocities are the same, and therefore their kinetic energies will be the same. So that's why the total kinetic energy is just 2 times the kinetic energy of a single one of them. Doing some algebra, this is what we get. Putting in some numbers, we get, first of all, note that Q1 times Q2 is negative, because Q2 is negative. K is 9 times 10 to the minus 9, so we get a minus, now 9, times 10 to the, 9 times 10 to the plus 9. Plus 9 minus 7 is minus 2, plus 2. Another minus 6 gets us to minus 9 times 10 to the minus 4. We have 10 to the minus 3 down here for mass, 1 gram, that's 10 to the minus 3 kilograms. And here we have 1 over D initial, well that's just 1 over 1, which is 1, minus 1 over a tenth, D final. 1 over a tenth is just 10. 1 minus 10 is 9, 9 times 9 is 81. This 1 minus 10 is minus 9, so that minus cancels this minus, giving 81. Then we have 10 to the minus 4 over 10 to the minus 3. In other words, 81 over 10, which is 8.1, and the answer is in meters per second. Now note that this is the velocity they both acquired as they fell towards each other, because they'll both acquire equal velocities, because they have the same mass and the same force is exerted on each of them due to Newton's second law. So they both are going 8.1 meters per second toward each other. Okay, homework problem 2. We'll do something similar, but a little bit backwards. Okay, I'm going to give the same two charges, Q1 10 to the minus 7 coulombs, Q2 minus 10 to the minus 6 coulombs. They've got the same masses of 1 gram, but this time they're going to start out 0.1 meters apart from each other. That's the close position. And they're going to start out with velocity away from each other. V2 is going to be moving to the right at 4 meters per second, and V1, well, it's just going to be moving to the left at 4 meters per second, so it's just equal to minus V2. And the question is, what is the final distance between them? And what I mean by this specifically is, what is the maximum distance between them, or what is the distance at which they stop and turn back toward each other? So we've been talking about electric potential, or voltage. You should now understand its relationship to potential energy, in particular that is defined as the electric potential energy divided by the charge Q of some test charge. And you should be able to deal with two special cases. One is the case of a uniform electric field where the change in voltage is minus the electric field times the displacement. And the other special case is the electric potential due to a point charge, which is equal to kq over r. So that's all for now. Have fun with this. Next up, we're going to talk about equipotential lines.